novel approach to implement a closed loop control power converter in thermal vacuum tubes. Today I shall be presenting a background, methodology, some of the results and final conclusion. When you look at these thermal electron tubes, which is very familiar to you, it's almost similar to transistor, but the difference is that these thermal electron tubes are used in high power applications. For an example, radio transmitters, X-ray machines, etc. And also here, if you look at the filament consists an anode and cathode. So this electron flow is crafted by the filament. So the filament is one of the key members of this unit. Particularly, the lifetime of the tube directly depends on the filament and its qualities or other properties. Now, apart from that, if you look at this filament supplier or other voltage supplier, so it plays a vital role when it comes to the lifetime of the filament or total thermal vacuum tube. Now, objective of my research was introducing a cost-effective closed-loop controlled filament voltage supplier to enhance the lifetime of powered filament tube. So, particularly, regardless of the power range of its operation. Now, in this application, what I have done is I have developed a self-controllable switching power supplier, which can produce ramp voltage output by varying the firing angle of thyristors with the time being. Now, here to generate the ramp voltage, I have used a power converter. So, the ramp voltage is in fact used as the power supply to the thermal vacuum tube. Now, so these are the properties which I incorporated in my design. So, this filament power supply resists to load and source fluctuations, and also here I initiated the supply voltage in uniformly increasing order or gradually increasing order, and also now this is a closed loop control circuit. Therefore, now output and the changes are constantly monitored throughout the operation, and also finally fault detection and diagnosis. Now, to present a solution, I have used some numerical specifications: maximum output current, maximum capacity, and full filament voltage of the supplier, power supplier, as 10 volt. Now, these are the waveforms for filament supplier. Sorry, the input to the power converter and output of the power converter. If you look at first one, almost it is AC power, which we can obtain to the power grid, and final one is the output voltage waveform of the power converter. Here, if you look at this output waveform, you can see that this conduction time is deferred, and the pulse width modulation is applied to obtain a different average value. Now, for an example here, since I have used thyristors, I can change the thyristor firing angle and defer this PWM value. Now, this is what expected average input voltage to the tube filament. In fact, this is the average value of the power converter output. So, this voltage supply variation is used to feed the power to the thermal vacuum tube. So, these are the integrated major components of my design. So, I designed one initiator circuit to create a ramp signal, and a pulse generator circuit, separate one, to generate PWM pulses, and also pulse amplifier to step up the input voltage, and also a synchronizer circuit and separate superposition circuit for fault detection, and also a communication platform. If you look at this integration of components. So this figure gives an overview. Now primarily, a single phase AC input voltage is fed, and this pulse generator amplifier and thyristor bank is used to generate required signal to apply for the rectifier. And after rectification, the signal is applied to the tube. Here you can see the closed loop nature of the design. Here, regulated ramp output voltage is constantly monitored through this controlling, synchronizing and supervising circuit. Okay, so this is a block diagram of my design. Now, previous one was an overview. Here, these components are separately implemented or shown here. You can see first one is we have T1 transformer and T3 transformer. For the T1 transformer, now regulated AC output voltage of the supplier is fed. Now that voltage supplier is sent through a voltage divider and AD532 DC converter to step down, and that voltage conversion is fed to non-linear input of a differential amplifier. From the bottom part, you can see that it's a separate circuit for a ramp signal generator or other an initiator circuit. Here, a separately ramping signal is generated and fed to non-inverting, so inverting input of the operational amplifier. Here, the output voltage of the operational amplifier is sent through pulse generator circuit for the PWM purpose, and also it is found that this PWM signal is not large enough, therefore I had to send through a pulse transformer. So thereafter an different pulse amplifier and separately located thyristor bank is fired. You can see the bottom circuit, it's the controlling and supervision circuit. You can see T3 transformer is again fed the same output controlled signal, and it is sent through AD532 DC converter, and finally it is sent through AD8561 dual comparator. It's an high-speed analog comparator which is often used in the industry. So this is the circuit diagram for the pulse generator in NI multi-chain, and this is the circuit diagram for the initiator and ramp circuit, ramp voltage generators. And so this is the entire circuit diagram for the complete power converter. When you look at the result, you can see that the ramp voltage output and pulse generator outputs are separately shown. So the first one is ramp voltage output, which is kind of gradually increasing one, and also this pulse generator output is separated for the pulse generator 1 and pulse generator 2. If you look at the output of ramp generator and comparator, well, you can see that in green color and blue color, which are the outputs of comparator. And finally, and this is the final one. This is final convert input and output voltage. Thank you.
Thank you. The subject is open for discussion. I will start. Why are you interested in thermal vacuum tube? Why do you develop such a thing? What is the application?
Initially, we wanted to apply closed loop control techniques to
No. why do you select thermal vacuum tubes? Is there a problem?
Yes. Okay. Now, when we look at the supply voltage of thermal vacuum tubes, more often we can see stepwise input. What we did
Now,
was,
how often do you use it? Is there a practical problem? What is the practical problem you are trying to solve?
yeah. Now, when we look at, it's depend on different applications. Now, depend on applications, there are ranges of power converters. But in our case, so this is targeted. I mean, this was initially targeted to using for a research lab, research work, which was conducted under the supervisor. So he wanted us to develop the power converter, which should be capable of generating a typical output waveform. At the first part, it has to be demonstrated with ramp signal, and final part, it has to be demonstrated as a steady state signal.
So why wouldn't you do it with modern power electronics rather than going for vacuum tubes?
Now, when we look at vacuum tubes, one of the critical point is that vacuum tube become weak due to irregularities of power supply and spikes of power inputs. So, in order to avoid that, we can use this kind of input waveform, or rather input power supply, and we can assure the life cycle of vacuum tube at a higher level, to a higher level. Sorry.
So now this vacuum tube should be using in high power transmitters as well as the X-ray generators. So they are also, we have some sort of power condition system. So how your approach differs from the existing models or existing systems?
When you look at commercially available power supplies, so they just use regular power supplies like, I mean, if you look at inside nature of the power supplies, so they are like boost converters, so I mean, they are in traditional way. Now in this particular case, the key difference is that we use closed loop control technique. The supply voltage and the output of the power converter is constantly being monitored every time when it is in operation. So in that field, when there is an irregularity or when there is a sudden change of the supply voltage, we can detect it.
Let us